Yeah, so I guess I'll pick up on one thread that Tom already touched on, which is the sense in which quantum gravity, oops, that was not supposed to happen, the sense in which the UV and the IR are connected in gravity. General relativity knows something about quantum states that I think has no analog in the in any other classical theory. But before I go there, I'd like to start by you know, I guess this is a high energy conference that we're at, and quantum gravity is maybe not the most obvious fit in every respect into what our field is doing, but I want to give it a little justification. So ultimately, we are all interested in unification. That's sort of the story of physics, and quantum mechanics and gravity are definitely our main remaining task there. And we probably all want to answer deep questions like how the universe began and why it began that way, what time really is, whether, you know, it's emergent the way that we see space clearly emerge in examples like ADS-CFT. What happens when you jump into a black hole? Can you even get inside? About 10 years ago, people here argued that you may not be able to jump into an old black hole. And even if you do get inside, what happens at the singularity inside the black hole when you hit that? What is our description of nature in such a situation? Okay. So the downside, we've got to be honest about this, of studying quantum gravity is that we are not exactly flooded with experimental data. And I want to sort of connect to that a little bit in this talk. So the opportunity that I see for us is that in recent years, this actually goes back to the work of Bekenstein and Hawking and some things that Tom already talked about, but we really see in recent years much more sharply that when we think about quantum gravity in a particular way, and the kind of hypothesis that we have made, which are just well-motivated hypotheses, they're just guesses. Those hypotheses have limits where you turn off gravity, you turn G Newton down, and you find highly non-trivial new results in quantum field theory, which you can actually then go and prove laboriously in quantum field theory. But it's, I think, quite significant that we didn't discover them that way, and that they kind of talk about a regime of quantum field theory that we didn't even know was perhaps that interesting. It's relativistic in the sense that light-like separated events play a key role in the statement of some of these properties. But at the same time, it's low energy. You don't need to have some kind of large center of mass energies in order to make these statements interesting. And it's very quantum. Those are statements about the behavior of quantities like the von Neumann entropy under variations of the size of some region, for example. So I want to first give you a cartoon example of a hypothesis of this kind, just because it's more familiar, and which goes back to the early 70s. But this is sort of the scheme that we've been following. We start with something that is a nice classical gravity theorem, which you'll find, you know, proven in all the textbooks. And then you'll also notice that all those theorems in the textbooks rely on something called the null energy condition, or on some other energy condition, perhaps a stronger one, which is not actually, you know, that condition does not actually hold in any relativistic quantum field theory. You can find states that violate this condition, and so you might worry that these theorems are worthless. But you can go ahead and guess some quantum corrected version of these theorems that might have a chance of still holding true. This is the point where we are going from something that's been mathematically proven, but using an assumption that we know is invalid, to something that's just a guess. And most of these guesses involve in some sense replacing the classical area of surfaces with a kind of quantum corrected area, given by still the classical area plus the von Neumann entropy of the matter on one side of that surface. So we're imagining some surface that divides the world into two parts, Cauchy splitting surface. And we look at one side of it and look at the von Neumann entropy, and we just add that to the area, and we stick here a 4 times the Planck length squared so that the dimensions work out. Yeah, so some of the time when you do this to a classical GR theorem, you get something that has an interesting non-gravitational limit. And I'll first give you again a cartoon example where we don't learn that much, but in some cases we've learned, completely new things about quantum field theory or quantum mechanics from this. So the warm-up example is Hawking's area theorem, which he proved in 71, and it's simply the statement that the total area of all event horizons cannot decrease. So when black holes merge, the new black hole has a greater area, for example, than the sum of the old ones. And as I advertised, this relies on the null energy condition. Yeah, I should say what it is. So it's a stress tensor twice contracted with any null vector. If you assume that is non-negative, then this kind of theorem follows. And of course, as I said, it's not true. And in fact, Hawking himself found the consequences of this fact a few years later when he discovered that the area of a black hole will actually shrink if you leave it alone. It will go down because the black hole evaporates. And this is indeed tightly connected to the violation of the null energy condition near the horizon. So in response to such a disaster, you might come up with what's called a semi-classical area conjecture. Actually, that's not what it's called. I'll tell you what it's called later. But I'll call it a semi-classical area conjecture as opposed to the classical area theorem. And all we're going to do is replace the classical area with this quantum corrected, add this quantum correction to it, 4gh bar times the entropy on the outside, in this case on the outside of the black hole. The relevant surface is some cut of the event horizon sometime. And we're going to look at the exterior. And then we might conjecture that Hawking's area theorem still holds if you replace this classical with the quantum corrected area. And then you could see if that's actually true for an evaporating black hole, and you'd find that yes, it is true. It is true because even though the area decreases as the black hole evaporates, it produces enough Hawking radiation to more than make up for that by some order 1 factor. And so this actually works. Now, of course, this is not how it was really discovered. Historically, this inequality was proposed quite a bit before Hawking discovered Hawking evaporation of black holes. It was discovered for different reasons, or proposed for different reasons, by Bekenstein in 1972, and it was called the generalized second law. And really, it was proposed in a form where you divide the entire equation by 4gh bar. Then the first term is the change in the area, the change in the entropy of the black hole, what's called the Bekenstein-Hawking entropy. And the second term is just the entropy outside. So that particular combination, black hole entropy plus entropy outside, is called the generalized entropy. What I call the quantum corrected area is really just a rescaled generalized entropy by 4gh bar. But I deliberately told the story in this ahistoric way because it could have played out that way. And the wonderful thing about this generalized second law or semi-classical area conjecture is that it's simultaneously a statement about geometry and quantum information, and that's sort of the recurring theme here. These things become connected. So in the classical limit, of course, you get back Hawking's area theorem, but there's also, and I think this was kind of underappreciated for a long time, there's also a non-trivial limit where you take Newton's constant to 0. So this is a regime, for example, where you have a black hole and matter is falling in, but the back reaction is negligible. It's maybe already a very big black hole. And in that setting, this generalized second law actually implies a statement about quantum mechanics. It implies the monotonicity of the relative entropy of quantum states. Now, it doesn't imply that in complete generality. It applies it for the kind of quantum states that appear in quantum field theory in settings where you have a black hole. And also, people in the 70s had proven the monotonicity of the relative entropy. If you don't know what that is, it doesn't really matter. It's some property that all quantum states have, and which is quite non-trivial, and it was hard work to prove it. And it's interesting that it follows from a theorem that you got by a guess about quantum gravity. Not a theorem, a conjecture, a guess about quantum gravity, in the limit where you turn gravity off. I think that's a wonderful example of how gravity somehow knows some stuff that's really deeply quantum. So here, again, this was a toy example. Even if people had noticed this back then, it wouldn't have been terribly new. I think monotonicity for relative entropy had already been proven. But let's go back to the general scheme and now apply it to something where we did get something new. Okay, so instead of the Hawking's area theorem, let's start with a different classical theorem. In this case, we're going to start with a fairly trivial statement in GR that matter focuses light. So this is something that's exploited in a large class of beautiful observations, lensing, microlensing, and so on. Matter makes parallel light rays start to move towards each other, not apart, for example. And the mathematical statement of that is a statement about what's called the expansion of a congruence of light rays, and I'll review briefly what that is. But first, I want to stress that, as usual, the null energy condition doesn't actually hold. We know that. And so we need to deal with that fact and see if we can replace this statement with one that survives given actual quantum field theory states in which the null energy condition is violated. So before I go there, let's just review quickly what the classical expansion is. So if you have some surface and there are light rays going away from it, for example, if it's a sphere and the light rays are going to the interior, then you would say the expansion is negative. If they're going to the exterior, it's positive. Parallel light rays have zero expansion, and so on. It's really a logarithmic derivative where you ask what happens to this area element as you transport it away from the original area. And this would be a space-time diagram. Now, in this diagram, I've already taken into account that I might be interested not just in the area as I move along the light rays away from my original surface, but also in what the entropy of matter fields is going to be doing when I do this, because I'm interested in replacing, this is my scheme here is going to be replacing area with quantum corrected area. This expansion is just a kind of derivative of the area. So we can do this. We can define a quantum expansion using this kind of substitution and then still taking an appropriate derivative. Let's call it capital theta. And it's the straightforward generalization. Maybe it's not 100% straightforward because you really have to think about functional derivatives to make it rigorous, but it's pretty obvious. So here's a picture. This might be part of the surface you started with, and then you deform the surface a little bit, maybe upward here, and you look at both how the area changes and how the entropy in the exterior changes, and take the appropriate derivative. So part of this scheme is to make a guess. We're going to make a guess about quantum gravity. And the guess is that we get to replace this classical statement that holds with a null energy condition by this quantum statement that holds for this quantum corrected expansion. Okay, so now let's see whether this guess is any good. Well, and it's in fact quite easy to see that it does a lot of things for us, whether it's right or wrong. But assuming it's correct, a bunch of results that we already thought hold follow from it in various limits. I won't talk about them here. I'll focus on the last one because it's actually new. And we did discover it this way. The quantum null energy condition. So this is going to be our reward at in a non-gravitational limit. We're learning something about quantum field theory. So let me tell you what it is. But let me first tell you how you get there. So this was this quantum focusing conjecture, the hypothesis of what we should replace the classical focusing theorem with. And we can unpack that, right? This quantum expansion really has an area and an entropy inside of it. And we can unpack it and collect various terms. And then we can take advantage of the fact that when gravity is weak, we can, for example, specialize to our initial surface being a plane in Minkowski space. Like, t equals x equals 0 or something. You've got a plane and you've got light rays going away from that plane. Those light rays initially have zero expansion, but due to the weak gravity that's still around, they're going to get an expansion that's of order g Newton. And that's great because there's a g Newton here as well. And And so what's happening with the judicious choice of initial surface is that these red terms are the only ones that survive. Basically, what you want to do is make sure that this otherwise leading term, the classical expansion, doesn't get any larger than the terms coming from the quantum corrections. Then you've got a G in front of every surviving term, so you can just cancel that out and formally take the limit where G Newton goes to 0, nothing happens anymore. And you get, these are the two surviving terms. I've just put one on one side and the other on the other. And one of those terms is the expectation value of the stress tensor. Again, this sort of null component of the stress tensor. And what we're finding is that it's bigger than some quantity that is given by a second derivative of the entropy on one side of the surface that we started from. So really what we're looking at is a surface. It has a point that we're interested in at. There are light rays that are going away from that point orthogonal to the surface. And the second derivative is with respect to deformation of the surface along that light ray. We're looking at one side. What is the entropy? How does it change? What's the second derivative of that change? That's what appears on the right-hand side here. And first of all, it's an interesting statement because we didn't really have any kind of lower bound on the local energy density in quantum field theory that didn't depend, and for which you didn't have to know all the details of the quantum state. Of course, this is still somewhat state dependent. You need to know what the second derivative of this entropy is, but that's the only thing it depends on. Conversely, you could say that if you think of sort of sweeping over space and getting more and more information by doing so, by putting more and more into sort of your half of the space, you can think of this as a statement about how rapidly you can gain information, or more precisely, the energy density that you're sweeping over. If it's positive, it helps accelerate the rate at which you're gaining information. If it's negative, then you're decelerating the rate at which you're gaining information. So this, again, there's no G Newton left. It's only an H bar here. This is a statement that you could, in principle, try to prove within quantum field theory. And the thing I want to just emphasize about that is that even for free fields, the proof is fairly complicated. There's like 20 pages like this that we had in our paper when we proved this. And we didn't know how to do it for interacting fields. Tom Faulkner and his collaborators figured that out after some earlier work using holographic methods. This is a real tour de force, and it builds on work by Tom Hartman and others. It's like 70 pages. So the reason that I'm emphasizing this is that we got this in 2 lines from the quantum focusing conjecture. Okay, I don't have time to talk about the fact that this is actually saturated. There's a really tight connection between information and energy density that's uncovered here. But what I do want to emphasize is that when we say that this was proven in relativistic quantum field theory, of course, that assumes that relativistic quantum field theory is the correct description of nature at low energies, at these kind of scales that we're discussing, for the kind of experiments that we would take to probe these regions with their null deformations. And we haven't, of course, probed quantum field theory in this regime at all. So in that sense, I'm confident that quantum field theory is correct in this regime, but in that sense, it's a prediction at low energies. And it's also pointing us to some beautiful new physics in a regime that I think we've largely not thought about that much. And the key thing here is that while, I think for those of us working in this field, we get sort of used to the fact that, of course, generalized entropy makes sense and we get to make all these conjectures. Ultimately, these are just guesses about quantum gravity. And we don't have a whole lot of feedback about our guesses about quantum gravity. So when a guess like that gives us a deep new result in quantum field theory, that's actually really hard to prove within quantum field theory, then at least indirectly, I think we can say that's telling us we're probably on the right track in how we think about quantum gravity. So I think that's encouraging, and that's what drives my outlook. What I've told you about is, of course, only a snapshot. It's a small piece in a larger web. You heard from Tom earlier today about some other pieces, and you heard yesterday, I think Juan was speaking and others. And this quantum focusing conjecture, the quantum null energy condition, plays a role that I didn't have time to talk about in many other portions of this web that we're currently spinning. And I think, well, I'm excited to see how this, how this web gets strengthened and filled in and better connected. At the same time, if I was allowed to really speculate about very long-term developments, it would be wonderful to start thinking about how you would actually probe quantum field theory in this low energy regime, how you would probe the vacuum. And, I don't know, it's probably easier than building a galaxy scale accelerator. So if it helps us, connect quantum gravity to the real world, that'd be a wonderful thing. So I'll stop there. Thank you.
Thank you, Raphael, for the very nice talk. Do we have questions in the room?
I can abuse my microphone privileges. Can you speculate about the experimental protocols? Can you say some ideas about what sort of experiment you might have in mind?
I think no. I mean, first of all, the reason that I said this is very long term is because I have no idea. I think what you would start with condensed matter systems, and you would try to, in fact, what we're trying to do is understand in what settings condensed matter systems emulate properties of relativistic quantum field theory well, and in which they don't. One thing that tends to get in the way a lot is rest mass. We don't like rest mass, so you have to find settings in which you can, in which that somehow cancels out or doesn't play a role. But yeah, so I think that would be the starting point before you actually try to go in and measure properties of the vacuum directly in the actual quantum field theory.
Thanks.
Thanks. So with the quantum focusing conjecture, you showed many results that followed. So are some of them equivalent statements, or all of them are, or the quantum focusing conjecture is the most basic thing that all follows?
Yeah. So the quantum focusing conjecture is stronger than all of these. That's right. So I mean, for me, this sort of journey started out with thinking about entropy bounds. You just sort of think about a twice integrated version, roughly, of this statement, right? You ask how much entropy can you have in some region of space bounded by some area, and then you discover there seems to be some sort of conspiracy. If you want to have a lot of information in some region, you need a lot of energy density to do it. The energy adds up and it causes some back reaction that prevents you from violating these bounds. And the quantum focusing conjecture, well, especially in the form of this quantum null energy condition where you have, the energy density on one side, not the total energy in some region, but just the energy density, and some second derivative of the entropy on the other side, is sort of the most local, most informative version of these statements. So it's not surprising that by taking various limits, you can get some older conjectures back.
I'm curious if there's something special about if you go to the equality regime. So if you take the quantum null energy condition, under what circumstances do I get an equality? On the right-hand side?
So that's the slide I sort of skipped. It's this one, yeah. So if your deformation, can you see if I draw here? Yeah. So let's say you have some null plane in Minkowski space. So this is supposed to be x equals t or something like that. Right? If I make a very narrow deformation, so this is my original surface, and then I make a very narrow deformation of this surface, and I have an interacting quantum field theory. This is not true in free quantum field theory. Then the inequality becomes an equality. This was first proven holographically by the first group of people, and then more generally by the second group, which again included Tom Faulkner and a bunch of my students and his student, I think. So yeah, so then it just becomes energy equals second derivative of the entropy. For any interacting quantum field theory with a conformal fixed point. What happens when the coupling goes to zero? There's a discontinuity. Yeah, and it has to do with like the number of twist 2 operators in the theory. The spectrum suddenly gets enriched.
Any further questions in the room or out there? If not, let's thank Raphael again.
Thank you.